we move on to question 4. We're supposed to draw slope fields on the axis provided. Now again, they said there's no graphs this year, so this, well, I might still do it. I guess here's what I'll do. I'm just quickly going to say what the slopes are for each point, so rather than draw them out, because they might do that as an FRQ question instead. If they can't actually make you draw it, they could indicate for certain points what the slope is. So I could format this better, but for sake of time, I'm going to write it like this. Point 0.02, we have dy dx. Actually, just make a table. Probably be the best way to go. So I'm going to start off with 0.02, and so that would just be -2, and we have the 0.01, that would just be the point -1. We also have 0, -1, that would be +1. All right, then we also have 1, 1. I guess I'll start at 1, 2 and kind of go in this pattern that I've started for myself. If I have 1, 2, that would actually be 0. If I have 1, 1, that would be 2 minus 1, which is 1. And then if I have 1, -1, looks like it would be 3. Okay, now again, all I was doing for each of these was just plugging in the x and y value into this expression and simplifying it. So let's see if I got that right. So -2, -1, +1, yep. 0, 1, 3, yeah, those look right. Yeah, so pretty much as long as you got all the slopes for x or 0 correct, that was 1 point. Slopes for x was 1, that was 1 point. So kind of a weird way of scoring it, but there we go. So you could expect to see maybe a table question like this. So for the indicated points, find dy dx. They could format the question like that instead. All right, let's move on to part B. So find d squared y over dx squared. Okay, well that's just going to be, now, I mean, I don't know if you want to finesse a little bit. You could say that that equals, I'm just going to take the really formal approach. What this is saying is you're just deriving dy dx again. All right, well, what is that? Well, if you derive 2x with respect to x, you're just going to get 2, like normal. And if you derive -y with respect to x, you're going to get -1 with a dy dx. Okay, but now notice that that's really 2 minus, well, dy dx isn't just a thing, it's actually a full expression. Okay, and so we can simplify that. So we can say d squared y, or dx squared, is -2x plus y plus 2. There we go. Okay, and determine the concavity of all solutions in quadrant 2. So I'll say in quadrant 2, x is always negative, and y is always positive. Which means, now I'm not sure how much I can really defend this, but which means d squared y squared x is greater than 0 for all points in Q2. So in Q2, all solution curves, just trying to use the wording of the problem. If you ever don't know what words to use in the problem, literally use the words in the problem. So if you kind of see what I did there. or I should say R, concave up. Okay, and we'll just keep going. So let's look at part C. We'll check everything at the end. So we have a particular solution with that initial condition. Does it have a relative minimum, maximum, or neither at 2? Okay, so this is kind of interesting because if we want to know whether it's a relative minimum, maximum, or neither, I'm just going to calculate two things. So obviously, we know f of 2 is 3. Now we can say f prime of 2 is equal to dy dx, and sometimes I write it like this, for x equals 2, y equals 3, which equals, well, if x is 2 and y is 3, then we have 1. And then, you know what we should also do? We should also look at f double prime. Now, technically I already know the answer because I just saw what this was when I plugged it in, but we should look at f double prime of 2, which is, again, d squared y over dx squared, evaluated at x equals 2, y equals 3. Now what's that? Well, I have this expression right here that's going to be negative 4 plus 3, which is negative 1 plus 2, which is also 1. Okay, so what's going on here? So since f prime of 2 does not equal 0, the point 2, 3 on f is neither a local min or local max. I guess we could also just say for the fun of it, 2, 3 is not a critical point, to use the correct vocab. So that's what's going on there. Now, let's say that f prime of 2 was 0. How would you determine whether it's a local min or local max? Well, you would look at the concavity, because if you have a slope of 0 and you analyze the concavity around that point, you'll know if it's concave up that it's local min, or if it's concave down it's local max. Alright, but since the slope isn't 0, it's neither automatically. Your slope is still increasing. You can't be a min or a max if you're still having some kind of slope. Okay, last but not least, part D. Now, I actually got a question about this before I made this video. This is the wackiest question that I've kind of ever seen. It looks so simple. I mean, it's just a line, and you have dy dx as a pretty simple function. But this is a very tricky question. So unfortunately, I've already kind of seen the answer, but it took me a little bit to try it out myself. But here's what I did when I came out swinging. First thing to notice is that, let's see here. If y equals mx plus b is a solution to dy dx equals 2x minus y, note y has a constant slope m, and dy dx is, this is kind of how I said it, of the solution, I should say solution curve, but so thus m equals dy dx. So that's super important to notice. Now, in other words, if you derive this you'll say dy dx equals m, is the short way around it, but that's a big note there. Now from there, the question is, what do you do about this? Do you call this m, or do you call this dy dx? Turns out the better way to go is to call this m. So I'm going to say it like this. So dy dx equals 2x minus y is equal to m equals 2x minus, and here's what I'm going to do now. I'm going to replace the solution curve. Alright, so instead of dy dx, I should write it like this, not equals, I should draw an arrow. There we go. Dy dx is m now, and 2x is still there, minus y, but y is now this mx plus b. So now is where things get even wilder. What we're going to do is we're going to say that 0 is what we get when we have 2x minus mx minus b minus m, and from there they do this wacky factoring step. But it makes sense. Let me explain it why they do this. Again, I'll be honest, this was not, I made a mistake somewhere. Oh, because, wait. Did I? No, I didn't. Okay, so they factor it like this because this is still an equation of a line, so to speak. Now, here's where things get really tricky, because you're looking at m's and b's and x's, and you're sitting there going, how can I solve for 3 things? Or in other words, as a student, you only ever can solve for 1 variable at a time, so how on earth are you going to get the solution? Here's what you're going to notice. M and b are constants. So what does that mean? It means for whatever value of x you plug in, you're always going to get 0. Now think about what that means. If this is 7, then you're going to get 0. If this is 25, you're going to get 0. If this is 0, you're going to get 0. Let's think about that. If you need to be able to plug in any number and get 0 here, then this slope has to be 0. You have to have 0x in the solution. So in other words, 2 minus m has to be equal to 0. That's the only way for no matter what value of x you plug in, this is going to be 0, guaranteed, because this is a constant. Remember, if m and b are constants, then this is not some variable that changes for different values of x. This is like 7, you just can't see it. So how do you get 0 regardless? Well, this is always 0. And then from there, that means m is 2. Well, if m is 2, now notice then, again, for any value of x, well, think about this. What if x was 0? Then now you just have this term left. How do you guarantee that you still have 0 if x is gone? Well then, b minus m must be equal to 0 as well. So, wait a minute. No, I did make a mistake somewhere. Where did I make my mistake? 2x minus y. No. Wait. Oh, that's why when I factored out the negative, I knew something was silly. That's embarrassing. Okay, anyways, so then you end up with b is equal to negative m, so b must be negative 2 since you know m. Okay, so again, wild question, wild ride. Sorry I made that silly mistake, but I definitely felt confident on this one. So again, it's not 0, not a critical point. So if x is less than 0, blah, 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 that's greater than 0 all the time. So different ways of stating that. But essentially the just reason is that it's always going to be positive in quadrant 2. So there we go.